Hi everybody, it's Jim Corkins and we are continuing on to week 7. So congratulations on completing your exam. And we're now moving to a part of the course where it gets a little bit easier, I think, in my opinion. So this part continues on from 2.0 from last week. Last week you studied Newton's laws. This week we are learning how to create free body diagrams. So you should have watched lecture 2.1 and 2.2, and now you're here at 2.1 tutorial. There are 6 pages to it, and it's about practicing those free body diagrams. And this goes along with lecture 2.1, as well as some parts of 2.2. So click on it, download it, and now we get into here. Okay, so here is the proper method of creating free body diagrams. So first of all, what I do is I list the from lecture 2.1 and 2.2. I'm going to go ahead over here and I'm going to list the non-contact force, which we learned was your weight. And that is the weight of the object, which is your mass times gravity. Then all the rest of everything is a contact force. Okay, and those forces are anything that they could be considered, anything that is physically touching the object. They have to actually touch the object. Otherwise, it's a non-contact force, and the only non-contact force in this class we're dealing with is mg. So those contact forces are just a general force like a push or a pull. So if there was a hand touching the object, I would subscript this force like subscript hand. And I would actually write out the word hand as a subscript. Some people like you to write just the sub h, but go ahead and write out the object, right? The next force is a string or a rope. So that'll be a force, a tension force. Another way it is written is with the capital T. And this is a string or a rope, and strings and rope always pull. Another type of force is it's a spring force. So you could put F sub S and spell out spring, or what I like to do is I actually like to just write in the equation. So I'm a big fan of writing an equation whenever you get a chance. So this is K times X, the spring constant times how far it's been displaced from the equilibrium position. And this is a spring force. Now, spring forces have 2 components to them. If it's compressed, it pushes back. A compressed spring pushes. And that's going to be a pushing force. A stretched spring will pull. So please watch 2.2 to learn more about that. Spring force. Okay. The final force is actually 2 forces. So a surface, if a surface is touching an object, it actually creates 2 forces. Okay. It creates a normal force. I'm going to call that F sub n. Your book labels this capital N, and I found out that students often will confuse that with the units of newtons, which is kilograms meters per second squared. But this is a normal force. This is just the ground or the surface holding up the object. And normal they mean is perpendicular to the surface. So this is actually the surface holding up the object, okay? Another type of force is the friction force, and that's going to be mu sub k or mu sub s times that normal force. And I wrote an n there, and I'm trying to break that habit. It should be times the normal force. So it's mu sub k or mu sub s. This is the force of friction. It's kind of a resistive force. and it's parallel to the surface. Now, what I've noticed is friction tends to be, especially if it does have a velocity vector, if the object is moving to the right, the friction vector is going to be pointed opposite that direction. So if the object is moving, that kinetic friction vector is always opposing the direction of the velocity vector. Okay? So in our force diagrams, I'm going to ask you to list the velocity and acceleration vectors, okay, given by the description too. So what I'm about to do is I'm about to teach you the steps to creating a force diagram using these forces that we've listed off to the side, okay? And this is a 2.1 tutorial, but this is one procedure to do all free body diagrams, okay? All right, so let's do this. So what we're going to do is we're going to look at the description and at the picture, and we're going to describe everything that is physically touching the object as well as the non-contact force mg. So we're going to list off everything that is touching this object, and we're doing a force or a free body diagram for the physics textbook, okay? So let's go ahead and start off by reading it. A textbook is pulled by a string to the right. So you see the hand pulling a string to the right, but it's being pulled but not with enough force to actually move it. Okay? So first thing that we are going to do is we're going to list off the non-contact force and get that out of the way. That way we could concentrate on everything that is physically touching the textbook. So mass times gravity, that always works in the negative y direction. Okay, that's always pointing straight down towards the bottom of the page. Okay. Now what we're going to do is we're going to list off everything that is physically touching the textbook. Okay. Now, one of the things touching the textbook is going to be the string. So see right here, it says a string is touching the textbook. The hand isn't touching the textbook. The string is touching the textbook. And we represent the string as a capital T, and it's pulling. And since the string always pulls, it's attached to the right of that textbook, it's going to be pulling it in the positive X direction. Okay. Now let's talk about everything else that is physically touching the textbook. While the string's out of the way, well, the surface is touching the textbook. So I'm going to list off surface. And the surface, again, has two different forces. It has one that is perpendicular to the surface, holding up the textbook. So that is going to be the normal force. And that is holding up the textbook in the positive y direction. Another type of force, which is always parallel to the surface, that is the friction force. Since this object is not moving, it's going to be a mu sub s. The s means that the velocity vector is 0, times the normal force. Okay, don't forget the normal force in that. Now, this is a resistive force. So if you're pulling this object to the right, that means friction is going to be resisting that pull. Okay, so friction is inherently resistive. If you were pulling it to the right and friction did break and it began moving, it would be moving to the right. Therefore, friction would be the kinetic friction would also be pointed to the left. Okay, so always think of friction as a resistive force. Okay. Well, now that I've listed off all the different types of forces acting on my object, I'm going to transfer them to right here. And I just increased the size of my window. So here we go. So what I'm going to do is, since I've used red, black, and blue, I'm going to use green to create my coordinate system. All right. So This dot is supposed to represent the center of mass of the textbook, and it's usually like a really small dot. So what I'm going to use is I'm going to use a dotted line, because the vectors that we're going to write are going to be solid lines. So I want to distinguish between those two. So this is a dotted line and another dotted line. In this case, since the surface is left and right, it's perfectly horizontal, this coordinate system, the x direction, is always going to be parallel to the surface. Okay? So I'm going to list also any forces pointed to the right are in the positive x direction. Any forces pointing up are in the positive y direction. Anything pointing to the left are in the negative x direction. Anything pointing down are in the negative y direction. So put a dot, put a cross through it, and then label it positive x, positive y, negative x, negative y. Okay? Now what I'm going to do is I'm going to transcribe these labels and these forces to this force diagram. Okay? So I'm going to start off with the mg force. That is, we have it listed as pointing in the negative y direction. So for right now, what I want you to do is I want you to attach the bottom of the vector to the dot, and the head should be pointing away from the dot. So since this vector is pointing down, the tail is attached to the dot and the vector is pointing down. And we're going to label this the mg vector, and I'm also going to label the direction it's pointing. It's pointing in the negative y direction. This is going to be important for later on. So if it's pointing in the negative y direction, label it negative mg. If it was pointing in the positive y direction, I'd call it positive mg. Okay, but it's not. Anyways, so now once I've got that force out of the way, let's do the tension force. That tension force, that string is a T force and is pointing in the positive x direction. So starting from the dot, I draw an arrow pointing to the right in the positive x direction. I'm going to label that positive T. I should put little vector heads on stuff. You don't have to, but I'm doing it because, you know, I'm an educator. The surface force, notice that I use the same color because the surface force is actually two different things. It's a normal force pointing in the positive y direction. Make sure I note that I got that out of the way. So the normal force is pointing in the positive y direction. So that's pointing up, and that is a positive F sub n vector. So I've got that guy. And this other one, which is the friction force, is pointing in the negative x direction. So I'm going to draw a vector pointing to the left, and that's going to be a pointing to the left, mu sub s because it's not moving, and the friction force. I got that. The last thing you're supposed to do is label the velocity vectors and acceleration vectors. Okay, in this case, the object is not moving in the x direction or the y direction. So off to the side, I'm going to list the velocity and acceleration is not moving. And I'm going to list the velocity and acceleration in the y direction as well. All right? So this is your force diagram. These are the steps to doing a force diagram. Again, the steps to doing a force diagram are listing off the forces that are acting on the object. You list off the non-contact force. And then once you have that in its direction, and once you have that, then you have to just go, what is physically touching this? Well, a string is touching it, and it's pulling it to the right. A surface is touching it, it's holding it up, but also that friction force is resisting the pull of the string. And then what you do is you draw a coordinate system through a dot, label that coordinate system, and then you transcribe these vectors to your free body diagram. Attach for right now, just attach the tail of it to the dot and have it the vector heads pointing away from the dot. Then what I want you to do is off to the side, label the velocity and acceleration vectors. Those are not forces, so you shouldn't attach those to the dot. And there you go. That's how you do a free body diagram. Thank you.